Hi everyone, thanks for
Hello.
joining us. I'm hoping that we'll start from quite a high level with Aron today around exactly what neuromorphic is, how it differs, and why it's important, and we'll get sort of into the weeds around how it's applied to AI and some of the other potential applications. And ultimately, I hope we'll end up on a sort of, prediction type of timeline-y questions. When is this important? When do we think this is going to hit the market? So I'll let Aron introduce himself first, and then I'll briefly talk about myself, and then we'll get into it. Aron?
Thanks, Lawrence. Thanks for the invitation. My name is Aron. I'm co-founder of SEMRON. We are a startup in Dresden, in Germany, a little bit south from Berlin. You probably know that Dresden is becoming one of the centers of microelectronics in Europe with TSMC and Global Foundries there. We are building or developing AI inference chips based on an own semiconductor technology, and so we are happy to dive into that a little bit deeper later.
Great, and I'm Lawrence. I lead research at a deep tech fund called Lunar Ventures, and I publish all of my work on a site called stateofthefuture.xyz. And I've done a lot of work into future of compute, new architectures, new type of substrates, and tried to look at the semiconductor supply chain. So looked quite a lot into neuromorphic and its potential. So I'd like to start extremely high level and just ask Aron, as the expert building here, what exactly is neuromorphic and how does it differ from what we might just consider a semiconductor or a chip, a logic chip today? How does it differ?
So von Neumann versus or
exactly.
In general, okay.
Yeah.
I think at this point you are a better expert than I am in that field. So in very high level, in memory computing versus von Neumann architecture, this was a guy called von Neumann who invented kind of the computer architecture we still use for most of the chips. And basically it's just we have a separate memory and separate processor where we calculate stuff and we have a store stuff, so it's separate, and so we have to move the data in between both places every time we would like to calculate something, and we need data from somewhere. So which is fine. For most of the time it was fine in the last 60, 70 years, but now it turns out that costs a lot of energy, because if you move data, you consume energy. And especially for artificial intelligence, we have a lot of parallel operations. And parallelism means you can do that very efficient, but not if you have to move all the data always in between two distinct places. So that's for Neumann. And in memory computing, of course, as the name says, it's starting to solve that with coming up with devices or circuits which can store and calculate at the same time. So we don't have to move the data between the both places.
So a sort of, in my mental model there is just the co-location of memory and compute. And obviously, the closer you are to the memory and the compute, the less you have to travel in terms of the latency there, as well as the energy you have to consume to shuttle the data around. The other key feature is this idea between analog and digital. And could maybe go into a bit of detail there, Aron, around all of our computing, or the vast majority is digital computation, which is what we have, digital computers. What exactly is an analog computer? How does it differ, and how does it relate to neuromorphic?
Okay, it's also kind of personal take on that, but let's get first into the big picture. Digital is just a signal with two different levels, so you all know that. I mean, we have 0 and 1, and this is something we can handle very well. And we also could handle that very well in the beginnings of compute, so that's why we have that. Ideally, we would calculate with analog signals because they are very efficient, because we can encode a lot of information in just one short signal or spike, for example, whereas with digital signals, we need a lot of time to encode stuff in that. But on the other hand, analog signals are very difficult to handle because you need to be very precise on that, and you have some impacts on that which you can't really predict or correct after that. And with digital, you all have these. You have all these options to check whether there's an error in it, which came from some I don't know, influences from outside or not, which is in analog way harder, as I mentioned. And that's why we feel like this is now the turning point where the electronic industry is capable of handling the challenges associated with analog computing. If that's true, then the future would be analog.
Right. Right. So the benefit. I mean, we think about the first ever computer was an analog computer, right? The difference engine by Charles Babbage. So it started with analog, with just waves and trying to understand, signals, voltage or temperature or any physical phenomena. But it doesn't scale and it's not reliable in the sense, right? I believe it was after World War II that we needed more reliable computers for planes and for analyzing locations of planes in the sky. And we needed to be more reliable. So you convert things to binary, 0 and 1. It's reliable, more scalable. Why then has there been a renewed interest in 2020 or before around analog computing? And what's changed in the preceding years that makes it viable as a new technology?
Yeah. I think it's mostly about artificial intelligence and that we figured out that we need to handle the energy inefficiency associated with digital compute.
So purely just we're using too much energy and we're looking for new solutions to use less energy.
Yes, and there's another, a second point, which is kind of more recent, but people thought about that 10 years ago already. I mean, it's kind of obvious for like calculating in an Excel sheet, we need a very high precision floating point. But it turns out, because of parallelism in artificial intelligence or deep learning models, we don't need that high precision in the operations, which is really into the favor of analog computing.
Could you explain that a bit more around the precision piece? So what do you mean in terms of why do we not need high precision, or explain what high precision means in that context?
I mean, an intuitive explanation would be we still would be able with our brain to recognize or recognize people, for example, if we just flip one bit in the picture, like a small part in what we see. If we flip that, or if we lower the color precision, we still would be able to say, okay, we're sitting in an audience and there's some stage in it or something like that. So we are very tolerant to small changes or to low precision or to reduction or even to noise. We are very tolerant. Like if you have a blurry filter in here, we would still be able to understand what's going on. So that means, in turn, that we can get rid of a lot of redundant information. I don't need to understand whether you're wearing a red or a blue t-shirt just to understand that you are human, right? And if you are having a deep learning model, which is the task is to recognize humans, then we don't need these kind of information. If you process it with a classical algorithm, you typically would keep the information because.
So you're saying you're processing a whole bunch of information that doesn't actually need to be processed in order to get to the level of accuracy that's required.
Yeah, actually, if you look at a structure of the deep learning model, which is kind of an algorithm, you have the layer topology with a lot of input activations, and you have like millions of that in parallel. And then you just carry out multiplications on that, sum it up, and put in a nonlinear activation over the result. But if you flip one of these activations, it doesn't make any difference. And if you lower the precision of most of the values in that, like from you just cut like the last digit in a value or something like that, it doesn't make any difference. The impact is just zero. So why should we compute more complex than what we need? And that's something we knew for like 10 years at least. Smart people probably longer than that. But now we really see that it makes a difference, especially when we saw generative AI in the last year, end of last year, because it turns out for large language models, it's even better, or they are even more tolerant to a lower precision than classical machine vision convolutional-based models.
Clear. Okay, so let's think that through. So you're saying, we'll tie it back to neuromorphic computing. So an analog generally, which is that it is not able to achieve high precision. It's it's a low precision technology, let's say, and up until now, we're running these neural nets and large language models with high precision computing and architectures. And now the job is to apply these algorithms to low precision architectures like analog and neuromorphic. Is that right?
Yeah, I mean, the funny thing is that NVIDIA and all these kind of GPU manufacturers are also having a default, not the default mode, but they have an integer 8 mode, integer 8 precision mode to carry out those models.
Could you explain that a little bit? What do you mean, integer 8?
So usually, if you have a GPU and you have like graphical applications, you have operations in a floating point precision, which means just a lot of. So how are the numbers called after the comma? I'm not a native speaker. You have a lot of
decimal after the decimal point.
After the point, decimal point numbers, and this is something you can represent with a floating point number, for example. But integer 8 means you basically have like 256 different levels where you can represent a value, but not more than that. And it turns out that you are completely fine with integer 8, and now most people think you are even fine with integer 4, integer 6 precision. So just having like 64 or 128 different states what a value can have on a certain point in an algorithm.
Clear. So effectively, you've just described there an ability, like a technique to be able to turn the high complexity into like MapReduce, like less dimensionality and therefore less complexity and therefore less processing that's required. Are there any algorithms at the moment that's using integer 8 or any other type of method to run a compressed neural net or a compressed transformer to be able to run on a neuromorphic chip?
Yeah, there are some. In general, we also have to distinguish between training and inference. You mentioned running that. I assume you're implying also inference with that, just carrying out these models, and so the model can does its job, like the task it is programmed for, which we call inference. For inference, you typically need not much precision. You are typically fine with less than integer 8 for most of the models we have today. There are some we have to go into the details a little bit if we think about quantization, post-training, pre-training, but leave that aside for a moment. For training, we still see that we need more precision, more exact numbers to train the model, to adjust the models for its task. But actually, most of the energy is consumed economically. Most impact is on the edge, which means if you carry out these models, it could also be cloud inference, but training, even though it's very expensive, is not what is a limiting factor here. Since 3-4 months, it turns out, okay, we will also see some scarcity in resources for training as well. But I would distinguish between the discussion of precision with training and inference.
Yeah, that's great. Okay, fine. So let's put aside the training in data centers for one moment and talk more about inference at the edge, which obviously has extreme low power requirements, especially if we're talking about smartphones or IoT sensors. So they have extreme low power requirements, space requirements, as in they need relatively small footprints. So this is where neuromorphic potentially has more application areas. Is that how you see it? And maybe you segmented there between training and inference. Is there other segmentations where you think it's most appropriate at the edge? Smaller devices, larger devices? How do you think about it?
Mm-hmm. Yeah. For me, the bigger picture is how do we get these new type of technologies into the market? So we need an incentive for that. It's not just fine to have like a chip in the market with twice energy efficiency and say, okay, people will take the switching cost and say that's fine. It turns out, especially for cloud, no, you have NVIDIA as kind of a monopoly or a monopolist on the software hardware integration with CUDA. So you get a lot of convenience if you have this monopoly for like developers using that chip, and if you can't match that experience, it doesn't matter how more energy efficient.
Right, 2x is not going to cut it when you're used to CUDA. You're not going to switch to a whole entire new chip, which is the Cerebras C2 problem at the moment, right? Their new chip, which isn't CUDA compatible. So,
yeah. So yes, you mentioned that we have some features, technological features in first place. We have to match in order to make a product, not just a technology. And you mentioned power consumption, of course, that's critical. That's why we're talking about that. But it's also the footprint, the chip area. I mean, it's not fine if you have an in-memory computing architecture, which is like 50 times bigger than a classical GPU. So the big advantage of the energy inefficient GPU is it is compact and it's well understood.
Right.
So to meet that, it's very hard. And if you have in-memory computing, and a lot of companies and startups struggled because of that, and if you focus just on one technical feature like energy efficiency, you will simply fail, or you will struggle a lot. So you also have to meet.
You would think that the market would, we are 15 times more energy efficient than running a Qualcomm W2 or whatever the latest chip is. That sounds like a good value proposition. You don't think so?
I think it's not enough because, first of all, if you have 50 times more performance for the same power, you also have to explain how you can decrease the cost. If you have a constant cost per performance ratio, you pay the same amount of dollar per like tops, then you would also just end up in like paying 50 times more for the chip if you have 50 times more performance.
Right.
So you also have to change that. So no, or yes, the answer to that is it's not just.
Not just. Okay.
It's not enough.
Clear. And okay, cool. So we're getting somewhere. So we've got a sense of how neuromorphic differs. The features in terms of low power, in terms of density, in terms of like footprint, and all of those features, predominantly for edge. We're talking here about inference, but you touched on there some of the restraints, as in the NVIDIA chips, CUDA. You're betting against Moore's law. It's pretty much I know it's breaking down to somewhat, but what we're saying is there's a whole new chip that I assume requires new algorithms or tweaking of existing algorithms. It requires a new supply chain. Like, talk to me about what are the restraints to this being adopted right now?
I don't think it's about the algorithms. With the existing algorithm, we have enough market opportunity with the features we currently think about or see on the roadmap of like smartphone manufacturers to have $1 trillion opportunity. So we are fine with the algorithms we already have. It will improve, of course, and we will see different types of algorithms spiking and whatever.
Well, hold on, sorry, to just go on to that, because I think it's quite important that when you mentioned spiking. So one of the big questions in the industry is, can you just run the existing algorithms that we know and love on new neuromorphic hardware, or do we need new entire algorithms to take advantage? Your claim there is that actually we should just use transformer models and port them, and that's fine?
I mean, we see that transformer models behave quite well or perform quite well in a lot of tasks. So
quite well.
Pretty well. I want to have the better models than that, but I think we have a market opportunity with these models, and then we will see better models. We definitely know that they are not smart as we expect them or expect them to level with humans, of course. So we will see new algorithms, but I think the biggest challenge is to make work what we already have, and not think about what we will have in like 3 years, because we are so far away or we are so far behind with the hardware that we first have to think about that. We can think about algorithms that are better fit to the hardware constraints, but I think it's a very, very it's not a very reliable path to think like that. Ideally, you have more flexibility in hardware by itself and not just like designing it for a certain kind of algorithm, because the algorithm will change anyway. Right. So there will be no point where we say, okay, that's the algorithm we go for the next 100 years. I see. We have to think about beyond Moore's law. I know there's a lot of dispute around that, but what we know is that we are hitting a physical limit, even if it's not now, but in like 10 years, and we probably get, when we have like atomic layer when it comes to like how small the transistor structures can be, and we put a lot of resources on that, billions of dollars to develop that stuff, and we get another 10x in like density of or how much transistors we can put on a certain area. Yeah. So and then we have the problem. If we had just 10x increase in the density, but we are talking now about 1,000 times bigger models, even now, then what can we do? That's something we have to change.
Got it. Okay, so what you're saying there is there's a roadmap, and if you can look on the IMEC website, for example, which the industry agrees that 2036 or 2034 or something, we know for each half pitch reduction, what happens sub 1 nanometer, we know exactly how we're going to get there. So we have a very good understanding for the next 10 years of the sorts of level of performance we can hope for from digital chips. But what you're saying is that's great, and we can continue on that line. But we know at some point there is a hard stop.
I would even say that's a kind of a lie, or a stopgap, or not. It's probably a dead end, I would say. I'm not sure whether we will put all these billions required for this roadmap actually when it's time. I'm pretty convinced it will not happen, because the problem is that the cost will not scale. Simply, it's all about the cost, and the cost is often overlooked because it's not sexy. It's a very, very boring topic, but it's actually what makes a difference.
Perfect for a panel. A very boring conversation. No, please.
Sorry for that, but actually that's what makes a difference between not just technology and product, but product and mass product.
Great.
And we have to have that for like chip production. So we always think about, okay, how can we decrease cost per performance by a factor of 100 or 200 or something like that. And that's nothing which is even...
What's the driver of cost? Sorry, Aaron. Because, okay, this is really important. What you're saying is it's not just this new magical technology. We need to really think about can we reduce the cost of the underlying of the compute. And you're saying well, it doesn't scale. Fine, we can technically build it, but economically there's no point. You're saying neuromorphic is, but what's the driver of the cost? Is it the energy? Do we go back to that von Neumann bottleneck? Like, why is it that, why can we get 10x less cost? What's the driver?
I mean, the promise of lowering the cost is that you put more transistors on a certain footprint without having more cost in variable cost, more variable cost in production. What we see when we see how that scales with mass costs in manufacturing, semiconductor manufacturing, we see that since I would say 7 nanometer, we don't see any decrease in cost per, let's say, transistor. And
7 nanometer is sort of roughly where we are. I think the A100, is the A100 7 nanometer? Or no, I think it's 5 nanometer process, right?
There's a lot of marketing involved in that.
Exactly, fine. But roughly we're talking about where we are with AI accelerators at the moment, which is 7, 5 nanometers, 4 nanometer N, I think it is, at TMC. But regardless, you're saying that, okay, let's go down to 3 and 2, but the cost will go up.
Yeah.
Well, we sort of see that with even the lithography machines that are required, the inspection machines. The cost is going up, right?
Yeah.
So what you're saying is you have to address the cost, and the sort of design that you're interested in building is actually the key pitch, the value proposition, as we spoke about, isn't it's more energy efficient. You're saying it's going to be cheaper.
Yeah.
Right.
I mean, I think it's not meant to be a marketing pitch here, right? But what we do is, so far, when we published in Nature Electronics our device, which we use, semiconductor device, which we use at SEMRON to build up a new AI chip, to date we are the most energy efficient semiconductor device ever built and validated for AI inference operation. But even with that, we don't see that as a unique selling point, because it's simply, first, it's a nice-to-have trap, and it's just a great technology. But we founded SEMRON to build a product. And that's why we think about cost, and our USP is we have the lowest cost per performance. And the simple trick about that is that we go the same way as a memory did in 10 years ago, when we saw the so-called 3D NAND flash technology popping up. And as the name states, it's just about we stack memory cells on top of each other. Mm-hmm. So we keep the footprint small. And actually, that's what we all have in our pockets in the smartphone. We already have in a micro SD card, we have like 200 layers of memory cells on top of each other. The good thing about that technology is that the most expensive step in semiconductor manufacturing, which is so-called lithography, is shared among all 200 memory layers. Yeah. That means you save roughly 150 times cost per memory cell, something like that. And exactly that's what we do with AI compute. We just take the memory, 3D memory, and put a device or a small modification in that, so it can not just act as a memory, but also calculate. So we turn a memory in an AI inference chip.
So to clarify, essentially the insight there is stack the memory on top of each other, which we already have with high bandwidth memory. That's not necessarily novel, but you're doing, what is it that enables you to do it now that couldn't be done 5 years ago? I'm sure it's not a unique insight. Let's just stack stuff on top of each other, use less space. Surely it's going to be better. So what changed?
So memory is low power, or memory access operations is low power operation. So if you stack something, you have higher density of something. Essentially, if you have 10 compute layers and you calculate 10 times more on the same, in that you have 10 times a higher energy density. And the surface is roughly the same. In the surface, you need to spread all the heat and the energy. So it becomes worse if you scale something in the 3D dimension, or in a third dimension. And with memory, that's fine because it's low power. With compute, it's not fine because it's not low power.
I get it. So memory could be stacked. That's easy because it uses less power. But with logic, you have a problem because it uses much more energy, and therefore you literally can't stack it because the thermal footprint would be ridiculous, right?
Yeah, and now we are in the resistive versus capacitive discussion, because so far what we did is to compute, basically we were just moving electrons. That's what we did. Whether it's in transistors or in so-called Aron-based in-memory computing stuff, which is analog, it's still that we move electrons. And whenever we move electrons, we create noise, and whenever we create noise, we consume energy. Mm-hmm. And it turns out that's a physical limit, and it turns out that it is too bad to have like meaningful scaling, 3D scaling of compute. So that's something we had to overcome, and that's exactly what we did when we started about. Funny story is, even though we started our journey in Dresden, in Germany, my co-founder and I, we actually met in Cambridge on a study trip, and we started discussing, okay, what can we do to overcome the threshold or the physical limit associated with moving electrons, basically. And then we thought, okay, why not doing it capacitive with a capacitor? Because we have electrical fields then, and they can also calculate in an analog manner. Why not just doing that?
Yeah.
I mean, it sounds a little bit more simple than it actually is.
Yeah, no doubt.
But it works, and actually it works quite well. But nobody needed that before, so nobody was thinking about that, which is our advantage.
So the demand side arrived with large language models and AI to be able to stack the logic. And okay, so let's sort of try and circle back to where we were, which is that the claim, or I think the renewed interest in Neuromorphic here is extreme low power, probably at the edge, and for AI inference, but also for other use cases. I'm very interested in event-driven cameras, for example, sort of cameras that effectively are passive until something happens in the camera in 1 pixel, and then is able to adapt and do processing at the edge. This is this idea of a sensor that is not just sensing, is doing some processing. So I think that's interesting. You could think about awake words, so extreme low power until you say, hey Siri, or whatever it might be. So there's a variety of use cases, but I want to sort of wrap up on like a final question which has been sort of bugging me for a while, which is, the main driver of, you mentioned a driver of cost is to do with, stacking these devices and stacking the modules and reducing the cost, but also it's just economy of scale, volume. And so the reason why the chips we get today are extremely cheap is because we produce billions of them on an annual basis, and we have these huge markets. But for Neuromorphic, it's a challenge because you need to know where the demand's coming from and the size of that market to then put in an order with TSMC to produce X number. And in order to do that, you need to prove the market. But you can't prove the market until you've reduced the cost of the chip. So how do you deal with economy of scale? Or what's the answer to getting the demand side to be able to produce it at scale?
Mm-hmm. You have to go to consumer electronics. Maybe automotive or cloud at some point. But as I mentioned, cloud is very difficult to attack because of NVIDIA right now and the software, not the hardware. And with the consumer electronics and even with legacy applications like smartphones or devices, you have like a huge market to produce billions of chips. Yeah, even though you have just a few players like MediaTek or Qualcomm who can do that, if you make it into that, you're basically done when it comes to scaling. And from there, you can go to different applications as well. You can go to cloud inference. You can go to automotive, which is not a very attractive market for a startup, to be honest. But you can also start creating new applications. I mean, one of the reasons VR headsets and smart watches, smart glasses, probably also smart watches, is not a huge market or mass adopted right now is because they don't provide the value we need in order to replace a smartphone or to accept paying more for another device. So we need to add more functionality.
I see.
And more functionality we only get with artificial intelligence in that case because we have a non-deterministic input. We have like gestures, we have language, so we don't have a keyboard anymore, which is in a smartphone. So we have to do something about that and probably can create these kind of mass market if we do something on the compute hardware side.
Interesting. Well, good. I'd love to talk more about that in particular, but I know we've come to time. So with that, if you have any questions after, please come up to myself or Aron. We'll be wandering around. And yeah, thank you very much for your time. Thank you, Aron. It's been a pleasure.
Thank you. Thank you.